Today we're going to begin talking about thermodynamics, and thermodynamics have to do with enthalpy, entropy, and free energy. In order to understand these three things, we're going to take an analogy of a car. On your dashboard, you're going to have three dials. One is called the tachometer, one is called the speedometer, and one is the fuel gauge. These three dials tell you something completely different as you're driving. If you're driving down the highway and you see a police car hiding behind a billboard, you're going to first look at your speedometer to make sure that you are not going over the speed limit. You really don't care about your tachometer at that moment. You don't really care about your gas. All you care about is your speed. But then down the road, since you are going the speed limit, you didn't have to worry about the police officer waiting there. You see another billboard and it says next rest stop 30 miles. So you're going to first look at your gas and make sure that you have enough gas. You don't really care about your speed at that moment or your tachometer. Lastly, if you're trying to learn how to drive stick, very often your tachometer helps you because it tells you the RPMs of your engine and when you need to shift. And so if you only look at your RPMs, it doesn't really tell you your speed, and it certainly does not tell you your gas. So the point is, these three dials are all different. They all tell you completely different things. However, they're related because the faster you go in your speed, the higher your RPMs, and the more gas you're going to use up. So they are related. So just like you have three dials on your dashboard in your car, you have three dials on your chemistry dashboard. One dial is your free energy, one dial is your change in enthalpy or heat, and one dial is your entropy. So let's understand each of those. Free energy is energy available to do work. It tells you if a reaction is spontaneous or non-spontaneous. A spontaneous reaction is going to occur once you get it started, and it will keep itself going. And that's called exergonic, and it releases free energy. A non-spontaneous reaction will not happen on its own. Even when you get it started, it's not going to keep itself going. That's an endergonic reaction, and it will absorb free energy. Quick example of that, spontaneous would be a match. Once you start a match, it's going to keep itself burning. And also rusting. Once something starts to rust, it's going to keep rusting on its own. Okay, sometimes they're fast like a match, sometimes they're slow like rusting. Remember, the only thing that tells you fast and slow is the kinetics chapter that we talked about with rate laws. But delta G tells you if a reaction is going to continue to happen on its own. So a negative G tells you it is spontaneous like a match or rusting. Now a non-spontaneous reaction could be something like cooking an egg. When you cook an egg, you have to keep it going. If you turn off the fire and take the egg off of the hot pan, the egg will not continue to cook because you have to keep it going. So that's a non-spontaneous reaction. Non-spontaneous doesn't mean impossible, it just means you have to keep it going. It's not going to keep itself going once it starts. Okay, delta H we've talked about before. That has to do with heat. Another word is enthalpy. So exothermic reactions are ones that release heat, and endothermic reactions are ones that absorb heat. Lastly, entropy has to do with randomness, getting more random or less random in a reaction. So if you think about burning a match, that gets more random because the organized match and the oxygen gas turn into all gases, and so it's becoming more random. A less random reaction would be something like, let's say, freezing of water. So it goes from a liquid to a solid. That's getting less random. So if you think about a match, it's a really good reminder of a spontaneous reaction. So let's look at the symbols for the plus and minus for delta G, delta H, and delta S for this process. A match burns spontaneously once you get it started. Remember, you have to provide the activation energy, but once you do that, it's going to burn. So that's a negative G, meaning it is spontaneous on your dial. Okay. Now, delta H has to do with heat. A match feels hot, so it's releasing heat. That's a negative delta H. And we just said that a match gets more random when it burns, so that's going to be a positive change in entropy. So when you do the math, a negative minus a positive guarantees that you are a spontaneous reaction. So if you have a reaction that releases heat and it gets more random, it is guaranteed to be spontaneous. Okay? Cooking an egg is the total opposite. To cook an egg, you have to put in heat. It has to absorb heat. So that's a positive H. Cooking an egg, it gets less random because it's liquid into a solid. So this is less random. And so when you take a plus minus a negative, you're guaranteed to be a positive, which means you're non-spontaneous. Again, doesn't mean impossible, it just means that you have to keep it going. It won't keep itself going. Now mathematically, if you had two negatives here or two positives, it could go either way depending on which one wins out in absolute value. So if they're both negative, okay, the one that favors spontaneity is the negative H. So that means that it has to be really, really exothermic compared to not getting too organized. However, if they're both positive, the thermodynamically favorable thing is the entropy, meaning getting more random favors spontaneity. So it has to be really, really getting a lot more random even though it's absorbing heat. And mathematically, if this wins, then the answer is going to be negative. So really all these are little dials on your dashboard to tell you if a reaction is spontaneous, does it absorb or release heat, and does it get more or less random. All right, so we're going to move this up, and we're going to just briefly talk about this. We're going to come back to this later, that the delta G, the exchange in free energy, is equal to negative RT ln K. K is the equilibrium constant. Okay, T is the Kelvin temperature, and R is this 8.31 joules per mole Kelvin, which tells you that G has to be in joules per mole, not kilojoules. And that's going to help you figure out the equilibrium constant if you ever had to relate the two together. Okay, so let's talk about equilibrium. If you're at equilibrium, if you have equal amounts of reactants and products, if K is 1, then your delta G mathematically would be 0 because the ln of 1 is 0. All right, if delta G is negative, meaning spontaneous, mathematically K is going to be a large number, and that makes sense because a spontaneous reaction is going to favor the products, and it has a negative G. The opposite is true if you have a positive G. That means it does not favor the products, and therefore you're going to have a small k, which means that that reaction favors the reactants. Now we're going to focus just on delta H, the heat dial on our dashboard. We've talked about this much already in the year. Enthalpy is, again, the change in heat in a reaction. You know that if a reaction absorbs heat, the delta H is going to be positive. If it releases heat energy, it's going to be negative delta H, which corresponds both to endo and exothermic. If there are two ways to write it. One way is to write it as a side note, as delta H equals positive something, that means it's endothermic. Or if you write it as a negative number, that means it's exothermic. And you could see from the graphs right here that an endothermic reaction is going to end higher than it started. It absorbed this much energy, in this case 68.1 kilojoules, and it's going to feel cold because it's absorbing heat. This one releases 196.1, so it ends lower by 196.1, so the change is negative, and it's going to feel hot if you were to feel that reaction. Okay, we talked about this before, that if you take a reaction and its regular delta H is 68, and then you double it, double, you're going to get twice as much heat needed to be absorbed, so that's 2 times 68 kilojoules. And if it absorbs going forwards, then that means if you write it backwards, it's going to release. So this one is going to be negative 68 because it's the backwards of this one. Also, you can follow stoichiometry with delta H. So if the delta H is positive 68, that means it absorbs. So one way, like I said, is to put a side note of delta H being plus or minus. The other way is to write it directly in the equation. So since this is endothermic, the 68 is on the left side. It's being absorbed. And you can follow the bridge with this. So moles is little bridge, so I would just do 3 divided by 1 times 68 is 204. Same thing with this one. If I had 34 here, I would little bridge it to the end, let's say. So 34 divided by 68 times 2 is 1.0. And then if you had grams, of course, that's the big bridge. So you do 48 divided by 2 divided by 32 times 68 is 51. So you can follow stoichiometry with H as well. Side note, if you wrote it backwards, okay, so if we're in negative 68 delta H exothermic, then that means the 68 would be written on this side, on the right. So either write it on the right, write it on the left, always as a positive when you write it in the equation, or as a side note, you write it as a plus if it's endo and a minus if it's exo. Now we're going to talk about finding the delta H of a reaction, which means the change in heat. In order to understand that, we're going to take a quick story. Let's go back to our bread and cheese, and let's say that bread costs 10 cents to buy, one slice of bread, and cheese costs 25 cents a slice, and we're going to sell our sandwiches for $1. The question is, are we making money? So common sense tells you, well, let's find out how much the sandwich costs to make. So 2 times a dime, because we have 2 breads, and 1 slice of cheese makes 45 cents. We're not counting labor, we're just counting materials. So 45 cents of materials, but we're selling it for $1. So yes, we're going up by 55 cents, and we're making 55 cents. Common sense tells you that you're going to take 1 minus 45, and that's going to give you your change in money. Your delta money is 25 or 55 cents, positive 55 cents. So you're making money. Okay, so let's suppose there's a guy down the street and he's not happy about this, so he wants to steal your business. So he says, you know what, I'm going to sell sandwiches for 40 cents and everyone will come to me. And he's right. He sells the sandwiches for 40 cents and everybody goes to him for a day until he realizes his mistake. Because every time someone buys a sandwich, it's like, here's your sandwich and here's a free nickel. Because he's losing a nickel every time he sells a sandwich, because you're going to do 40 cents minus 45 cents. So the delta money for him is negative. So the analogy would be an endo versus an exothermic reaction. An endothermic takes in heat, and exothermic releases heat. So now, we already knew the cost of the bread from our story and the cost of the cheese and the cost of the sandwich. So how do we find the, quote, heat cost of different elements and compounds? We need to look in appendix in the back of the book, A19. So you could pause, find that page in the back of the book, and now we're going to look in the back of the book and see what we find. If you scroll down all the heat values and look for all the zeros, you're going to see that you have a 0 kilojoule heat of formation for elements in their standard states. So for instance, carbon normally, first of all these are elements, carbon, oxygen, fluorine, bromine, and these are their standard states. Carbon is a solid at room temperature, oxygen is diatomic because it's Hanoff-Goldbriat and it's a gas. Also fluorine is Hanoff-Goldbriat and it's a gas. Bromine happens to be Hanoff-Goldbriat as well, but it's a liquid. So anytime you have an element in its standard state, it has a heat of formation of 0. Because what we're saying is, how much energy does it cost to make this element from its element in the standard states? 0, because it already is an element in the standard state. But let's suppose we looked up a compound like CH4, methane gas. You'll see CH4 gas has a negative 75 kilojoule heat of formation. So what does that mean? To form 1 mole of methane gas from its elements in their standard states will release 75 kilojoules of energy. And you would need 1 carbon, and you would need 2 hydrogen gases. Again, all the blue highlights are elements in their standard states. If you want to make 1 mole of carbon dioxide gas, you look up the number, it's negative 393.5 kilojoules, that's the heat of formation. Again, that came from 1 mole of carbon solid and 1 mole of oxygen gas. Now, if you're going to talk about water as a gas, water vapor, that's going to come from an H2, remember it's diatomic, and half of an O2. And I know you don't like to see this 1/2 here, but the reason why is because you have to have a 1 right here. It's not a heat of formation reaction unless you have 1 mole of something from its elements in their standard states. So when you're looking up in the back of the book, I'm going to call this Bob, back of the book. When you look up in the back of the book, you're going to find the heat of formation. And just like we did with our sandwiches, you take the end minus the beginning. So look up the heat costs of all these. We looked them up already. This is negative 75. This is 2 times 0. This is 393.5 negative. And this is 2 times negative 242. Again, those are from the back of the book. Of course, you'd be given a chart. And now you're going to do the math. And you're going to see that the left side adds up to negative 75. The right side adds up to 877.5. And you take the end minus the beginning. And there's your delta H. The change in heat is negative 802.5. Of course, this tells you this is exothermic because it's a negative delta H, and that makes sense because if you go back and look at this reaction, you'll recall that this is combustion. Methane is what comes out of your gas jets at home in your stove, in the classroom, the gas jets. You don't have jets at home, but you know what I mean. Your stove, your dryer, perhaps your hot water heater, it's methane gas. So it's combustion, and that's going to release heat, so that's exothermic. So one way to find delta H is by Bob. Back of the book, products minus reactants. Another way to find it is by bond energy. So what you have to do here is you have to draw the Lewis structures for each of these. So let's take the same equation and do it with bond energy. So CH4, here's the Lewis structure. O2, here's the Lewis structure. And we have two of them, so I put a 2 to remind myself. Carbon dioxide, here's the Lewis structure. Water, here's the Lewis structure. We have two of them. Now you got to start looking up these bonds. How much energy is stored in this bond? So a CH single bond, if you look at this chart, is 413. So there's 4 of them there. An OO double bond is going to be over here, and that's 495, but there are 2 of them total. CO double bond in carbon dioxide is tricky. You can't just go to this one in the chart. It has an asterisk that sends you down here to tell you, oh, if it's CO2, it's actually 799. So you're going to go to 2 times 799. And then lastly, an OH single bond is 467. So there are 2 of them in the molecule, and there are 2 molecules, so a total of 4 of those bonds is going to be 467. Then what you need to remember is brokendoformexo. Brokendoformexo. If you break a bond, it's endothermic. You have to put in heat to break all these. And then you form a bond, it's exothermic. You're releasing heat to make all these. All right? So that's what you have to remember. Another way you could remember it, I personally don't favor this way of doing it, but you could remember reactants minus products. I don't like that because it might mix you up with the other one we did before, which was products minus reactants. But bond energy is the only one like that. Anyway, you take these positive, these negative, get the answer, negative 824. Again, it's exothermic. It's fairly close to the negative 802.5. Ideally, they would be the same number. They're not exactly, but they're pretty close. Lastly, stoichiometry also works with delta H, as we said before. So if they this is called a heat of combustion, by the way, because it's a heat of a combustion reaction. So the heat of combustion of methane is negative 802.5. Because there's 1 mole here. Again, it's for 1 mole of that thing burning. So you can also follow the bridge. So little bridge for moles, this divided by 1 times that is that. And then you could do grams, big bridge, 16 over 2 over 32 times that is that. And again, stoichiometry follows with kilojoules as well. Now we're going to turn our attention to free energy, which is delta G, and that is again the available energy of a system to do work. And there are 2 possibilities. Either the free energy is negative, which means it's exergonic, it releases free energy, which means it's spontaneous, or it's endergonic, which means it's positive, it absorbs free energy, it is a non-spontaneous reaction. Again, this is one of our dials on our dashboard, delta G. It tells us if a reaction is spontaneous. We learned in the other page how you can do products minus reactants using the back of the book, which is Bob, back of the book. And you can use Appendix A19 to find the G values or the H values or the S values. So you can actually find delta S, delta H, or delta G with the back of the book. So what I did here is I wrote all the back of the book numbers, and G is green. So this is negative 24 in the back of the book. 0 because it's an element in standard state, negative 394 for carbon dioxide, and negative 229 for water. Those are the green numbers. The yellow numbers are going to be for delta H, and the black numbers are going to be for delta S. So it's always the end minus the beginning. Remember to use coefficients. So 3 times negative 394, 4 times negative 229. We're going to subtract that by, or take away from that, negative 24, and 5 times 0. So when you do all that math, you get negative 2074 kilojoules per mole. This is a negative G. Remember what G tells you? That this reaction, since it's negative, is spontaneous. It tells you nothing about heat, tells you nothing about entropy. It's only free energy, which means it's spontaneous since it's negative. Now if we take our attention to delta H, it's the same thing. Here's the back of the book for propane. This is what you would burn in your grill outside if you have a gas grill. And this is an element in standard state, so it's 0. Negative 393.5 and negative 242. When you do the n minus the beginning, you get negative 2044.5 kilojoules per mole. So let's remember what that tells us. This is delta H, that tells us heat. So this tells us that this is negative. It's exothermic. So let's remind ourselves what this tells us. This tells us it's exothermic because it's a negative H. This tells us it's spontaneous because it's a negative G. And that should make sense to you because once you light your grill, it keeps itself going. You don't have to keep relighting it, ideally. Of course, if it goes out, that's a different story, but that's not because of this not burning. This will continue to burn if not disturbed at all and if it has plenty of oxygen. Okay, now we're going to turn our attention to delta S. and it's the same deal. You're going to notice that the black numbers for S do not have a 0 for the element in the standard state because every compound and element has some sort of entropy, which means randomness. The only thing that has no entropy at all is a perfect crystal at 0 Kelvin, which is pretty much impossible. So you're going to do your end minus the beginning again. You're going to get a positive number here. And remember what that tells you, that since it's positive, that means you are increasing in entropy, which means you are increasing in randomness. And that makes sense because if you look at this equation and you count the number of gas moles, you have 6 gas moles on the left and you have 7 gas moles on the right. So you're getting more gas, so that makes sense. Okay, gas is the most random of everything, so we'll talk about that in a minute. Now what we're going to do is we're going to take a look at our information we got and compare it. We found delta G, back of the book. We found delta H, back of the book. We found delta S, back of the book. We could also find any one of these from the other two using delta G equals delta H minus T delta S. So let's take the H and the S and calculate what the G would be from them. So here's the H. Here's the temperature. You always have to use Kelvin. Always, 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 always use Kelvin whenever you're putting an actual temperature. Now, here's the deal. You have to realize that this is in kilojoules, and that's what we found here, but this is in joules. That's no good. You've got to match these units. You can't put unmatching units. This is exactly the trap that many students fall into. Don't be that person, okay? Match units. So I chose to put it all into kilojoules right here. Okay, whatever you want. You could put them both in joules. It doesn't matter. So you have to match the unit. And then when you do the math, you're going to get this number of negative 2,075 kilojoules per mole. And this really matched nicely with the delta G we found using the back of the book. So they're both the same value really within sig figs, which is excellent. That didn't happen with the previous example I did with the bond energy. It wasn't that close for the delta H, but this one came out really nicely. Okay, last but not least, we're going to talk about predicting the sign of delta S. So even without the back of the book, you can predict what's going to happen in terms of entropy. So let's take a look at this. This has one solid. So what you have to remember is gas is the most random, followed by aqueous, followed by liquid, followed by solid. So if you have, just count the gases. Forget everything else. Count the gases. If one side has more gas, that automatically wins for entropy. So let's look over here. One solid, no gas. This is 0 gas. Okay, 0 gas. And this is 1 gas. So that tells you right away this side wins. So we're increasing entropy when we go this way. We're increasing entropy because we're getting more random. Okay, let's look here. We have 3 gases right here. And we have 0 gas on this side. So clearly, as we go to the right, we are decreasing in our randomness or entropy. Okay, so gas always wins. Hypothetically, if you had 1 gas on one side and you had 100 solids on this side, of course I'm exaggerating, it wouldn't matter. The gas always wins. So whoever has more gas wins. If there's not a different amount of gas, they could be equal or 0, then look for aqueous. The more aqueous wins. If that's a tie, then go for liquids. If that's a tie, go for solids. So that's the order that you're going to look for in entropy changes.